Welcome to Module 1 of our course on Machine Tool Theory. In this part of the course, we will begin with the most important topic of our safety in the machine shop. A machine shop is a place of precision, creativity, and productivity, but it is also a place where sharp blades, high-speed moving parts, electrical systems, and heavy materials coexist. Without proper awareness and discipline, accidents can occur in an instant. 1.1 The philosophy of safety. In a machine shop, safety is not simply a set of rules posted on a wall, it is a culture. It's a mindset where every decision, every movement, and every process is filtered through the question, is this safe for me, for the people around me, and for the equipment I'm using? Good safety practices. Protect the operator from harm. Protect the machinery from misuse or damage. Protect the quality of the work by preventing errors that could ruin materials. A safe shop is an efficient shop. Downtime from accidents, even minor ones, disrupts workflow and can lead to costly repairs or project delays. 1.2 Personal protective equipment, PPE. When entering any workshop, the first line of defense is yourself. This means wearing the right PPE. Safety glasses or face shields to protect against flying chips, sparks, or splashes. Hearing protection in environments with prolonged high noise levels, such as grinding or milling. Appropriate clothing, no loose sleeves, dangling jewelry, or scarves that could get caught in moving parts. Steel-toed boots for protection against falling heavy objects. Gloves, used with caution. Gloves are useful for handling rough materials but should never be worn when operating rotating machinery like lathes or drills, as they can be pulled in. 1.3 Machine guarding. Every machine in a professional shop is equipped with guards, physical barriers or covers designed to prevent contact with moving parts. These must never be removed or bypassed for convenience. Machine guards. Keep hands away from cutting tools. Contain debris, preventing it from flying into the work area. Reduce noise in certain applications. If a guard is damaged or missing, that machine should be taken out of service until repairs are made. 1.4 Housekeeping and shop layout. A cluttered shop is a dangerous shop. Good housekeeping means keeping floors free from oil, grease, and chips to avoid slips. Storing tools in designated places. Ensuring electrical cords and air hoses are organized and not tripping hazards. Maintaining clear walkways and emergency exits. The layout of the shop should allow for safe movement of both people and materials. Machines should be placed with enough clearance for operators to work without interference. 1.5 Safe operating practices. Some universal rules for operating any machine tool. Always receive training before using a new machine. Understand the machine's operation manual. Check that all settings, fixtures, and clamps are secure before starting. Stand in a safe position, never in line with rotating parts or directly in front of potential projector parts. Keep your attention on the task, avoid distractions. Turn off machines before making adjustments. Use the correct cutting tools, speeds, and fits for the material being worked. 1.6 Emergency procedures. Every machinist must know the location of emergency stop buttons on machines. How to shut off the main power supply. Where the first aid kit, fire extinguishers, and awash stations are located. Procedures for reporting accidents. Transition to next section. With a solid understanding of safety, we can confidently move to the technical side of machining because once you are safe, you are ready to measure accurately. Section 2, Measurement in machining. Intro tone, precise and methodical. Measurement is at the heart of machining. A part is only as good as the accuracy to which it is made. Precision measurement ensures that a manufactured part will fit perfectly into an assembly and perform its intended function without failure. 2.1 The role of measurement in manufacturing. Every machine shop job begins and ends with measurement. At the start, to determine raw material dimensions and plan the work. During machining, to check progress and make necessary adjustments. At the end, to verify that final dimensions meet specifications. In machining, we often work with tolerances, small allowable deviations from nominal dimensions. For example, a shaft specified as 20.00 mm might have a tolerance of plus or minus 0.02 mm, meaning any measurement between 19.98 mm and 20.02 mm is acceptable. 2.2 Types of measurement in machining. Linear measurement, length, width, thickness. Angular measurement, angles, tapers. Surface measurement, flatness, roughness. Geometric measurement, concentricity, parallelism, roundness. 2.3 Common measuring instruments. Vernier calipers measure inside, outside, and depth dimensions with accuracy to 0.02 mm. Micrometers, highly accurate instruments for measuring small distances or thicknesses, often to 0.001 mm. Dia indicators measure small movements, often used for machine setup and checking runout. Height gauges measure vertical dimensions or mark workpieces for machining. Combination squares measure and check angles, flatness, and depth. 2.4 Precision and accuracy. Accuracy refers to how close a measurement is to the true value. Precision refers to how repeatable and consistent measurements are. A machinist must strive for both accurate and precise measurements to ensure quality work. 2.5 Sources of measurement error. Errors can come from instrument wear or miscalibration. Environmental conditions, temperature changes can cause material expansion or contraction. Operator errors, incorrect reading of scales or applying too much force. To minimize errors, calibrate instruments regularly. Measure in a controlled environment. Use proper technique, gentle, consistent contact with the workpiece. Transition to next section. Now that we have safety and measurement in place, we can move into the actual process of cutting metals, which forms the core of machining operations. Section 3. Metal Cutting Technology. Intro tone, confident, explanatory. Metal cutting is the controlled removal of material from a workpiece to shape it into the desired form. It's both a science and an art, requiring understanding of material behavior, tool geometry, and cutting parameters. 3.1 The mechanics of metal cutting. When a cutting tool engages with a workpiece, a thin layer of material is sheared away in the form of chips. This process involves shear deformation in the work material, friction between the tool and chips, heat generation at the cutting zone. 3.2 Cutting tool materials. Cutting tools must be harder than the workpiece and able to maintain hardness at high temperatures. Common tool materials include high-speed steel, HSS, tough and relatively inexpensive. Carbide, harder and more heat-resistant than HSS. Ceramics, excellent for high-speed finishing of hard materials. Diamond, the hardest known cutting material, used for precision finishing. 3.3 Tool geometry. Cutting tools have specific angles designed to reduce cutting forces, improve chip flow, minimize wear. Important angles include rake angle, controls chip flow. Relief angle, prevents the tool from rubbing against the workpiece. Cutting edge angle, influences tool strength and finish quality. 3.4 Cutting parameters. Three main parameters control the cutting process. Cutting speed, the rate at which the cutting edge moves relative to the work surface. Feed rate, how much the tool advances per revolution or stroke. Depth of cut, thickness of the material layer removed. Choosing the right combination is crucial for efficiency, surface finish, and tool life. 3.5 Types of metal cutting processes. Turning, using a lathe to produce cylindrical parts. Milling, using a rotating cutter to remove material from a workpiece. Drilling, creating round holes with a drill bit. Sawing, cutting materials into sections.